All right, guys, so welcome to part two. We stayed right over here. And before we continue, you might notice that, of course, the vector for the velocity is pointing like right out of the circular motion, right? So how is it possible that the planet doesn't continue or follows the path of the vector of the velocity? Of course, it happens due to the gravitational pull that is exerted between the sun and Earth. So what would actually happen if we turn off gravity at some point? Of course, this is something totally imaginary. But of course, in the simulation, it's something that we can actually take a look at. Here you go. So basically, if you turn off a gravity and we don't have centripetal force anymore, nor the gravitational pull between both objects, then Earth will only follow the path of the vector of the velocity, which in this case will not follow the circular motion. All right, so let's continue. And let's talk about the uniform circular motion. A uniform means constant. Circular means that the object follows a circular path. And motion means there is movement. And also we have a little bit more about the centripetal force to expand it, and it means centered seeking. There is a force acting towards the center of the circular path. Even though the velocity vector points out of the ellipse, the centripetal force changes its direction, which influences the object to follow the circular path. Pretty much what I was telling you about. And remembering the graph that we just saw, the arrows that were colored in light blue were pointing towards the center of the object, of course, and then that will actually generate the centripetal force. Here you have another example, which is related to the experiment that we did at the beginning of the year, in which I was actually, turning a bottle of water without a tap at the top. And of course, the water won't come out. So all of that is due to the centripetal force. And we have this image in which different vectors are identified. For example, the vector of velocity that is pointing out of the circular motion, the centripetal force that is pointing towards the center of the ellipse. We have a gravity on water, gravity on the bucket, and of course we have the circular path that it necessarily needs to follow. Right, now we're going to go to some application problems, and just like I always tell you, make sure you keep track of all of the equations and formulas that we take a look at during the application problems, so later on you can actually use them to solve some other problems. And problem number one, Ivan and Eddie are riding a Ferris wheel at the Dade Country Fair. If the radius of the Ferris wheel is 10 meters, and it rotates once every 35 seconds, what is the linear speed of Ivan and Eddie? So we have our first formula right over here, in which we're going to have our distance is going to equal 2 times speed times the radius. And we're going to have also the time, which is going to be 35 seconds. So in order to find our velocity, we are going to use the following formula: 2 times speed times the radius divided by the time. After you substitute the values that you have in the equation, you are going to find out that the result is that the velocity of the Ferris wheel is going to be of 1.79 meters squared. Okay? Oh, meters per second, I mean. All right, so let's continue. And now we are going to talk about centripetal acceleration. Since the velocity vectors constantly change direction, by definition, they are accelerating. And this is something interesting to analyze as well. So we have our following formula in which AC is going to represent the centripetal acceleration, B is going to represent our linear speed, and R is going to represent the radius of the circular path. Here we have an application example. So Matt is driving his car around a curve that has a radius of 45 meters. If his speed is 25 meters per second as he negotiates the curve, find the centripetal acceleration for the curve. So It's pretty simple. We just need to write down our givens from the problem. We already have our linear speed, which is going to be 25 meters per second. And we also have our radius in the circular path, which is of 45 meters. So based on that, what is our centripetal force? We are going to use our formula. Acceleration in the, of course, centripetal acceleration will equal our linear speed squared divided by the radius. So one more time, you substitute the values. Our linear speed is 25 meters per second. You are going to elevate it to the second power and divide that by the radius, which is 45 meters. So what is the result at the end? So a centripetal acceleration will equal 13.9 meters per second squared towards the center of the curve. And something interesting to analyze right here is that whenever you are actually elevating any number with also the units to any power, the units are going to be elevated to that specific power as well. So what does that mean? So we have meters elevated to the second power will be meters squared. We also have seconds. Seconds elevated to the second power will be seconds squared. So the result right over here will be a meter squared per second squared. But you can actually notice that in the result, we only have meters per second squared. So what happens to the other meters? Well, you also need to remember that we are dividing our value by a certain unit that is meters as well. So whenever you have the same unit, let's say, at the top and at the bottom of your equation, then they can eliminate each other. So you are going to divide meters squared divided by meters, then you are only going to have one of the units, which will be meters. That is the reason why we only have meters per second squared. And units are extremely important in physics, so you can know what you are talking about, of course. Then let's continue. We also have an example for centripetal force. It is a force that influences an object to mean a circular path. It can be due to string tension, electrical force, gravitational force, or even more. The equation for the centripetal force in this case will be the following one, in which Fc is going to be representing centripetal force, m is going to be mass of the object, v linear speed, and last we have r, which is one more time the radius of the circular path. And we have an example right here. Ryan is swinging a 0.011 kilogram ball tied to a string around his head in a flat horizontal circle. The radius of the circle is 0.4 meters, and linear speed is 1.3 meters per second. Find the centripetal force acting on the ball to keep it in the circular path. So what's interesting about it right here is that we already have our formula, so we just have to substitute everything. We have our givens, which will be meters, which will be the mass, also the radius and linear speed. So we are going to be substituting in the equation for centripetal force, which is mass times the linear speed squared divided by the radius. And here is another interesting thing, of course. After you operate everything inside the equation, you are going to find out that you are going to have, as a result, kilograms times meters per second squared. So what is this, actually? Because remember that our mass is represented in kilograms, our radius our linear speed in meters per second, and lastly, our radius in meters. So what is exactly this value? Well, this is translated into newtons. So if at any time you multiply, of course, these units in that specific order, or in that specific situation, kilograms per meters per second squared, then you are going to have, as a result, newtons. And of course, what is our numerical value? Will be 0.046 newtons toward the center of the circular path. It's another important thing to keep track of in your list of formulas. Okay. I guess we have another example right here. There you go. So we have a circular force due to friction. Friction is a force that acts in the exact opposite direction of another force. It's something that we have studied before as well. It keeps cars in a circular motion during a race. If it was not for friction, cars will continue moving in a straight line. And the equation for friction in this case is going to be pretty simple. And Ff is going to be frictional force, Fn will be the normal force, and lastly, the coefficient of friction is going to be represented by this symbol that reminds us of a letter M, let's say, or an inverted Y. Here we have an example. Friction provides the centripetal force necessary for a car to travel around a flat circular racetrack. What is the maximum speed at which a car can safely travel around a circular track of radius 50 meters if the coefficient of friction between the tire and road is 0.25? Here we have another formula, and I will let you know the way we found out about this in a moment. So our new formula is velocity equals the square root of the coefficient of friction times the radius times gravity. So here we have our substitution of values. And one more time, it's very important that you keep track of all of the values that we are constantly talking about and about the units that we have right here. So for our velocity at the end, we are going to have as a result that it is going to equal that velocity is 11 meters per second. All right, so let's continue. Continue right here. All right, and this is what I wanted to tell you about. Combining formulas. Combining formulas is something extremely important in the physics world because you can use what you know from one topic to solve problems from another topic. So this is related to the previous problem, and I want you to pay very close attention to what we are doing right here. So frictional force equals the centripetal force. All right, so we already have this one, but this is just not enough. So which is the equation for each one of them? So the equation for centripetal force is the one that we have on the left. Mass times linear speed squared divided by the radius. And what is the equation for the frictional speed? Is the coefficient of friction times the normal force. But we can still expand our normal force. So what is the equation for our normal force? It's going to be mass times gravity. Okay, so right over here we have like the complete equation, let's say. So after we have this, you have to notice that mass is on both sides of the equation. So it can be removed. We are going to remove mass from the left and mass from the right of our equation. And at the end, we are going to end up having the formula that you see right over here. Linear speed squared divided by the radius equals the coefficient of friction times gravity. And basically, this is what we used in order to solve our last problem in there. So we were just reorganizing our formula, and we left our value of linear speed alone in order to find out about the values that we have right there. All right, so now let's continue with our last problem. A centripetal force due to weight. The gravitational force between two masses is directly proportional to the product of the two masses and inversely proportional to the distance between the masses. And here you have our equation. It's basically the equation for the that we have studied before regarding the universal law of gravity. And here you have an example. The gravitational force between the Earth and Moon provides the centripetal force necessary to keep the Moon in orbit. What is the average speed of the Moon as it revolves around the Earth? So here is another tricky thing. We were combining some other formulas, and our result is the following one that we have right over here. So velocity equals the square root of our constant gravity times Earth's mass divided by the distance. After we operate everything, we get as a result that the speed of the Moon will be 1,020 meters per second. Okay, guys, so that's about it for today in the lesson. Any questions, you can let me know during the live session. It's been great seeing you around. Goodbye, and all.